ladies and gentlemen, we're going to do 9.1. We're going to be doing the calculus version of sequences now that we've talked about some reminders from pre-calc. So our objectives today are that we're going to list the term of a sequence. We're going to determine then whether a sequence converges or diverges. But before I forget, I want to go back and talk about an example that we were doing from our precursor lesson. And we were, see if I can draw that. For example, in our precursor lesson, we were talking about if I want to sum this particular partial sum, right? So let's say it's from A to B, okay, just because. And we were talking about why doesn't the summation equal the area under the curve? Because it really resembles or looks like what we have done in the past. But as I've been thinking about it, driving back and forth to Tucson and in the funky weather, I started thinking about the reason that it doesn't match our integration techniques is because if I take the area under a curve, remember that I am taking the area under a continuous curve. For a sequence, it is not a continuous curve. It is a collection of individual data points, which is why when we tried to integrate, we didn't get the same value. So that just popped into my head while I was driving, so I thought I would mention that. Alrighty, so the first thing that we're going to do is we're going to be talking about generating terms of a sequence. And we did this in our precursor video, but some of our sequence equations looked much easier, so I wanted to present them the way our book is going to present them. So maybe the first one says B sub n is equal to, and oftentimes they will put this little guy in brackets as well, n over 1 minus 2n, and so they would put the rule in the brackets. And then if I substituted my numbers in, I would get 1 over 1 minus 2 to the first. And then the next term would be 1 minus 2 to the second. The next one would be 1 minus 2 to the third, etc., etc. And then that would generate this set of terms, negative 1, negative 2 thirds, negative 3 fifths, and then negative 4 sevenths, and then on our sequence would go. Another example, if I can get my paper going straight, might be, let's say C sub n, put this little guy in brackets, is equal to n squared over 2 to the n and then minus 1. So if I substitute my values in to generate that sequence, and yes, you could put these in your calculator and you could generate these terms in your calculator, I would get 1 squared over 2 to the first minus 1. Then the next one would be 2 to the second over 2 to the second minus 1. And then it would be, oops, I forgot that one, 3 to the second over 2 to the third minus 1, etc., etc. And then if I actually got my physical terms, it would be 1 over 1, 4 over 3, 9 over 7, 16 over 15, etc. Okay? Another way that you might see a recursively defined, and we talked about recursive means that it is in terms of the previous term. So remember we said this is a way to define a sequence that's in terms of the previous term. Sorry, I couldn't spell previous there for a second. Okay? So let's say we talked about this in our last video, but sometimes it looks like this. So we're going to have a sequence. It's not an equals yet. And then I'm going to know that the first term is equal to 25. And then here's how the notation looks a little bit different. It might be the next term is equal to the previous term minus 5. So again, it's not that different from what we talked about before, but instead of saying u to the n is equal to u to the n minus 1, this one says the next term is equal to the previous term, take away 5. So I just wanted to show you that notation because sometimes recursive formulas can look a little bit different way. So the next thing that we're going to talk about, the next subject that we're going to talk about, is this concept of convergence and then divergence. So if we talk about convergence, that means that the sequence, and I'm just going to write it like this, if I take the limit of my sequence and the limit or the sequence approaches a value, so let's say that my particular sequence approaches a value, then we would say that the sequence converges. If, on the other hand, I have a sequence and the limit of b sub n, let's say it doesn't exist, okay, and there can be a variety of reasons why that limit wouldn't exist, then we would say that a sequence diverges, which means that the limit of the sequence doesn't exist. All right, so we've kind of talked about that a little bit. Let's talk about next the properties of sequences, properties of limits of sequences, properties of limits of our sequences. Okay, so the first one, we're going to have to set up some conditions. So we're going to say we're going to let the limit of the first sequence as n approaches infinity, which would mean the infinite terms of the sequence. We're going to say that the limit of that sequence is L, and we're going to say that the limit of a second sequence as n approaches infinity is going to be k. So that's our given information. And I know that these properties are going to seem very much like common sense because they're not that different from information that we've talked about in the past when we've talked about limits. But it doesn't hurt to restate it. So the limit of a sub n plus or minus b sub n, which would mean if I added two sequences together, which seems kind of weird, but there you go. So then this would be the same thing as taking the limit of that one and adding it to the limit of that one. The next property would be if I take a limit and I multiply a constant by my sequence, and then I take the limit as n approaches infinity, then it's going to be that same constant times whatever the limit was in the beginning. Okay? The third property would be the limit as n approaches infinity of a sub n times b sub n, which means that I would take one sequence and multiply it by a second sequence, and logic would have that that would be what we get when we multiply the two sequences together. And then the last property at this point is going to be the limit as n approaches infinity of a sub n divided by b sub n is obviously going to be L divided by K. All right, so the next thing that I would like to do is talk about some converging or diverging sequences. So our example that we're going to start with is we're going to determine convergence. Remember, that means that the sequence converges to a limit or divergence. All right, so we're going to do this with three of them at the beginning. So the first one, we'll call it A. I'm going to have my sequence A sub n is going to equal 3 plus a negative 1 raised to the n. Well, if I forgot the other bracket guy. If I do that and generate the terms of the sequences, notice that I would get a 2, a 4, a 2, a 4, and then it would keep going, okay? So because these values are alternating between 2 and 4, we would say that this is an alternating sequence. And it kind of resembles sine and cosine. So because as n approaches infinity, they bounce back and forth or oscillate between a 1 and a negative 1, there's no limit. Same thing for here. Since this is an alternating sequence, it has no limit. So therefore, we're going to say that the sequence a sub n is going to diverge, okay, which is kind of a weird word. But there you go. Alrighty, the second one that we're going to do, we're going to have a rule for b sub n. My brackets tend to get worse as time goes on. Then this rule is going to be n divided by 1 minus 2n. And if I generate a few terms of this particular sequence, okay, it would be difficult to tell. So instead of generating the terms, I'm going to take the limit. So I want to do the limit of n over 1 minus 2n as n approaches infinity. And we remember how to take limits. So I would divide each term by n. So this is going to be the limit as n approaches infinity of n divided by n over 1 over n minus 2n over n. And if you'll remember, this guy's easy. He goes to 1. This guy goes to 0 because that would be the horizontal asymptote. And then this guy is going to go to a negative 2. The limit is therefore a negative 1/2. And since the limit of the sequence, I'm going to call b sub n as n approaches infinity, is a negative 1/2, since it approaches a specific value, then we would say that the sequence converges. Okay? We're going to be using these words a lot in this chapter when we're talking about either convergence or divergence. All right, so the next example that I want to do, same basic process, let me pull my paper down so you can see, is going to have a rule. We'll call this guy c sub n. And then his rule is going to be n squared over 2 to the n minus 1. And so instead of generating all the terms of the sequence again, I am going to take the limit. Well, if I take the limit as n approaches infinity of n squared over 2 to the n minus 1, notice that I would get infinity over infinity, which is the indeterminate form, which means that I get to use L'Hopital's rule because then it makes my life a little bit easier. So now I'm going to take the derivative. So this is going to be the limit as n approaches infinity. And remember, I'm using, maybe I can squeeze it in, almost there, L'Hopital's rule, okay? So I'm going to take the derivative and I'm going to get 2 to the n over the natural log of 2 times 2 to the x. Remember, the derivative of this guy is I have to use like my change of base, so it's the natural log of this guy times 2 to the x. And then if I had had something attached to my x, then I would have taken the derivative of that, but I don't. But when I do this, I still get the indeterminate form. So I'm going to take the derivative again. So then it's going to be the limit as n approaches infinity of 2, that's nice, over the natural log of 2 times the natural log of 2, oops, I forgot the 2, times 2 to the x, okay? And then if you'll notice, if I cleaned that up just a little bit, this would be the limit as n approaches infinity of 2 over the natural log of 2 squared times 2 to the x. Well, this is going to grow larger and larger and larger. This guy's just a constant, so we kind of don't care. That means that it's going to approach 0, because as the denominator gets infinitely bigger, then that means it's going to converge to 0. So then we would say that the sequence c sub n converges, oops, it only has one n, sorry, converges to 0. Alrighty, a couple of things we also need to remember as we start our chapter with sequences is I need to remember that n factorial is going to equal 1 times 2 times 3 times 4 onto infinity, and then n would be the last term. And then I need to remember a special case that 0 factorial would be equal to 1, okay? And then I'm going to show you some other special situations while my thingy refocuses, just to make sure that we remember notation. 2 times n to the factorial would be 2 times n factorial, which is 2, and then I would have times 1 times 2 times 3 times 4, etc., etc. But on the other hand, if I have 2n in parentheses and then factorial, then this would be 1 times 2 times 3 times 4 until I get to n, and then I would have n plus 1, and then I would stop at 2n. And so that would be 2n factorial. And while I'm there, I'm going to show you a couple of problems where I have to simplify things, and then we'll go back and finish just because it's a little bit unusual. So the first one would be I want to simplify n plus 2 factorial over n factorial. So if I did this, this would be n factorial times n plus 1 times n plus 2, because the n plus 2 would be the last term of that particular expression. And then I would have my n factorial in the denominator. Those two guys cancel, and then I get n plus 1 times n plus 2. So that one wasn't horrible. So now let's do one more of these simplifies. Let's do 2n plus 2 factorial over 2n factorial. Okay, so this is going to be, I'm going to have a 2n factorial, and then I'm going to have a 2n plus 1, and then I'm going to have a 2n plus 2. This would be the next to last term. This would be my last term, and then this would get me all the way to here. Okay, and then I would divide by my 2n factorial. Those guys cancel, and so it would just be 2n plus 1 times 2n plus 2. And this is a little bit unusual to think about, and we'll do an example in a minute when we talk about some more convergence, but I wanted to show you those while I was there. All right, the next topic that we're going to go back and review is the squeeze theorem. We talked about this in Calc 1, and we talked about it again this year at the beginning. And I'll show you a diagram. So here's kind of what the squeeze theorem says. So if I have some graph, and I have this equation, which might be 1 over 2 raised to the n, and then this one, which is a negative 1 over 2 to the n, and then in between, I have this oscillating function, and maybe this guy is a negative 1 to the n over n factorial. As n approaches infinity, it is being squeezed. Oh, look at that. I wrote the wrong word. Sad day. E-E-Z-E. There you go. It's being squeezed in between these two particular functions. The trick is finding what's squeezing. And so then, as you notice, as this approaches positive infinity, and as this one approaches positive infinity, they would approach 0. And since these two approach 0, and they are squeezing this function, then the limit of this function as n approaches positive infinity would also be 0. So that's what the squeeze theorem says. So instead of writing out the formal definition, I think we will just use an example to talk about convergence. It's a little bit unusual, so we'll just have to be patient as we work through this. So we want to show that the sequence that I have c of n is equal to a negative 1 to the n times 1 over n factorial. That's a factorial. So notice that this guy is going to make the signs alternate. So it's going to alternate between positive and negative. So before I can show that the squeeze theorem actually works, I have to find two convergent sequences that can be related to the given sequence. All right, so since we already have these two in our diagram, the two sequences that we're going to show, or that we're going to use, are 1 over 2 to the n and a negative 1 over 2 to the n, okay? And we're going to show that it squeezes this, and then therefore they have the same convergence. Alrighty, so we've already talked about both of these are going to converge to 0. And a mathematical reason for that would be as the denominator gets increasingly bigger, both functions are going to get closer and closer to 0. Okay? Just a word of reminder, I guess, an FYI. The factorial function in factorial grows faster than an exponential. So let's say x to the n. So a factorial function is going to grow faster than an exponential function. So just in case you haven't thought of that, that would be a nice thing to remember. So what I'm going to do is we're going to take the limit as n approaches infinity of, sorry, I'm reading my notes in a bad way. So I want to compare n factorial with 2 to the n. And you'll understand why we're going to do this in just a moment. So if I look at n factorial, this is 1 times 2 times 3 times 4, and then times 5 and 6, and then it goes on forever. Alrighty? So if I look at these first 4 terms, and I picked 4 at random, it wouldn't matter which number of terms I chose. Well, the sum of these, or sorry, the product of those is 24. And then I would have the rest of my sequence, which would be 5 and 6 all the way out to n. And that would be for n is greater than or equal to 4. So this would be the first 4 terms, and then this would be n is greater than or equal to 4. Well, if I look at 2 to the n, I would get 2, 2, 2, and 2, and then I would get 2 and 2. So if I look at the first 4 terms, and this would go out to a 2, so it would be a number of 2's, then this is 16, and then it would have, the 5th term would be 2, the 6th term would be 2, all the way out to 2, for n is greater than or equal to 4. So since I'm looking at both of these particular expressions from 4 on, notice that this sum, sorry, I keep saying sum, this product is greater than this product. So because that is true, this is almost like a proof, this implies for n is greater than or equal to 4, okay? And if you'll notice, why did we choose 4? Well, if I stopped here, this would be 6, and if I stopped at the 3rd term, and this one would be 8, and it kind of defeats my purpose. So I needed to get to a point where the first sum is greater than the second product. All right, so I'm going to take this expression, and then I'm going to write 2 to the n is less than n factorial. Okay, so then by the squeeze theorem, that means that a negative 1 over 2 to the n, oh, where'd my computer go? Hang on just a sec while I bring it back. There it is. Let me get him all back in the right place. A negative 1 over 2 to the n is less than or equal to a negative 1 raised to the n over n factorial is less than or equal to 1 over 2 to the n. And since that is true for n is greater than or equal to 4, and since these two converge to 0, then we know that the limit as n approaches infinity, right at the bottom of the page, of a negative 1 to the n over n factorial is going to converge to 0. Okay? So there we go. And then I also want to talk about, notice another thing about what we've done. Notice this statement right here. So notice that I have a negative of an expression, and I have a positive of an expression. So since we've talked about those converging to 0, a negative and a positive of the same expression converging to 0 actually talks about the absolute value, because it would take away the oscillation. So then the absolute value thing says that the limit of the absolute value of a sequence, which means that it would no longer oscillate because I have a negative 1 raised to a power, is equal to 0. So then that means that the limit of a sub n as n approaches infinity is also going to be 0. Alrighty, and this would be an application of the squeeze theorem. All right, that's it for today. We'll do the second half of 9.1 tomorrow. See you soon.